Hello, everyone. This is Mr. A. We're going to talk about solving absolute value applications, real-world applications. So this video is for anyone who was absent during this notes, or they just want to get prepped for the real-world problems that are going to show up on my test. So on Google Classroom, we have some completed versions of these notes and a blank version of these notes. So if you're missing those pages, you can at least follow along by grabbing those there. Please fast forward. If you're looking for a specific question, this video might end up long, so skip around, see what you really need, or just watch the whole thing. We'll see. To begin with, we're starting with blueprints. So the side view height and width of a building is mapped on a coordinate grid. We want to install a gutter at y equals 7.4. Y equals 7.4 is a horizontal line at approximately a little less than halfway between 7 and 8. So maybe about there, maybe a little less than that. So that line might be the gutter that's on the roof right here. So if that's the gutter line, what equation could we use to determine the x values of the roof line that hit the gutter? So we need equations. We need equations for the roof line. We already have the equation for the gutter, y equals 7.4. So what's the equation of the roof line? Since this is in the absolute value section, well, an upside down v looks a whole lot like an absolute value function. So what do I see here? I see its vertex is right there. That is a vertex of 6, 9. How do I get to 6, 9 from the parent function? So recall the parent function is y equals absolute value of x, centered at 0, 0. So how do I move a vertex of 0, 0 to 6, 9? I do right 9, up 6. Or sorry, right 6, go to the right 6, up 9. And then how do we do that in an equation? Then I would have y equals the absolute value of x minus 6 on the inside moves us right, plus 9 on the outside moves us up 9. The whole graph is opening down, so I know it's been reflected with a negative multiplied out front. Its slope, well, if I pick some really strong values like this one and this one, or that one, then that would be 1, 2, and 1, 2, 3, 4, 5. So 1, 2, 1, 2, 3, 4, 5. In both directions, we have negative 2 fifths to give us our absolute value slope. This is an a value, a vertical compression in the negative direction, so a negative vertical compression. So that's our equation. We need to find out at what values do we hit the gutter? At what x values does the edge of the roof intersect the gutter? How do I find the intersection of two equations? I set them equal to each other. So we have y equals negative 2 fifths times the absolute value of x minus 6 plus 9, and have that set equal to 7.4. If I solve this equation for x using the usual steps, isolate, check if it's possible, split it, then these should be the intersection points of where these two hit. So isolate, minus 9, minus 9. And we have 7.4 minus 9 is negative 1.6 equals negative 2 fifths times the absolute value of x minus 6. Get rid of the negative 2 fifths by multiplying both sides by its reciprocal, negative 5 halves. And the 5's gone, 2's gone. Negative is positive. We are left with the absolute value of x minus 6 equals. Negative times negative is positive, so 1.6 times 5 halves is 4. Very clean answer. So we check step 2. Is this possible? Or absolute value function equals a positive number 4. This is absolutely possible, so we could say that in a couple ways. 0 doesn't equal 4, so that's one case. That doesn't work. But positive numbers come out of absolute values as well. And positive numbers, well, there is a positive number that definitely equals 4. So this is possible. Let's find out when it happens. We take the absolute value of x minus 6, and we split it up, well, equals 4, and split it up into its two possibilities. This is how we get rid of absolute value bars. We say x minus 6 equals the original, and x minus 6 equals negative 4, the opposite. Solve for x by adding 6, and we get x equals 10, and x equals 2. So where does the gutter hit the roof line? Turns out I made this problem perfect, in that it will hit exactly at the side of the building at 2 and at 10. That's where we intersect. Turns out the gutter is exactly as long as the edge of the building, which is kind of nice. There's a couple of ways we could solve this. One, if you want to, you could go into your calculator, literally graph this equation and graph y equals 7.4. These two equations, the roof line and the gutter line, your calculator can find its intersection, and it would be 10 and 2. Or take a simplified version of this expression, the expression absolute value section. Once we simplified it and got the absolute value bars all by themselves, the equation is the absolute value of x minus 6. And then it equals 4. This should also give us our intersection points. So that's just a graph. The absolute value of x minus 6, that's a graph that shifted right 1, 2, 3, 4, 5, 6. Actually, to make this even more clear, let me put this on a nice to scale graph. And then we could super see exactly where this hits up. So you could do this by hand if you had graph paper. We have the absolute value of x minus 6, so it's got a vertex of 6, that's up 1 over 1. It's got a slope of 1, so that's going to be somewhere there, somewhere there. Let's graph this high enough to where it's going to intersect with 4. So we have the absolute value of x minus 6, and the function f of x equals 4 is just the horizontal line at 4. So if you graph this on really neat graph paper and you graphed it exactly to scale, like as accurate as you can, you would also get the intersections 2 and 10. So you could do this by hand, you could plug this in a calculator, you can use the simplified expressions, and even better, when we ask that question, is this possible? Well, of course it's possible. The only way that it wouldn't be possible is if our horizontal line, because this absolute value goes on forever and ever, the only way that it's not possible is if we have a negative horizontal line, something that this graph doesn't even intersect. That's why we can't equal negatives. Well, that's one of the many reasons. So, that's problem 1. We would say, what x values do we intersect? At the x values, x equals 10 and x equals 2. The roof intersects the gutter. Okay, and now we'll move on to the next problem. Okay, tables. We can do absolute value functions from graphs. We could do it from tables. We could do it from descriptions. In this case, we have both a description and a table. Anytime I'm given a story, a real-world problem, I like to draw pictures just so I can visualize it in my head. So the moon has a relative velocity of 1 kilometer per second with respect to the surface of the Earth. So I prepared, and I have a moon. Whoa, too big. Shrink that down. I have a moon, and I have the Earth. Not super to scale, but it'll fit, at least. So what do we have here? The moon, obviously, orbits around the Earth. And it's going at a velocity of 1 kilometer per second. So how fast is it orbiting around the Earth? 1 kilometer per second, it's telling me. Relative velocity. Using Houston as time 0 seconds. I'm pretty sure we're using Houston because I stole this problem from NASA. Using Houston as time 0 seconds, the students completed the table below showing the relative surface distance of the moon from Houston. They keep using this word relative as a function of time. Negative time represents time before reaching Houston. Positive time represents time after passing over Houston. So let's say I can guesstimate about where Houston is. Let's put it right maybe there. It's not super accurate. Let me rotate this thing just a tad. There we go. Now it's lined up slightly. So the moon is hovering right above Houston at some point in time. And what is it telling us? When time in relation to Houston, 0 seconds, the moon, they're telling me, has a relative surface distance from Houston of 0 kilometers. I think that means that we're not talking about the distance that the moon actually is away from the Earth. We're talking about its relative distance. What could that mean? Well, we're talking about time it's passing over the Earth and not passing over the Earth. So we need to show its orbit just a little bit. Let's see how well I can draw a circle. Good enough. So we got a circle. That's kind of ugly. See how well I can make this circle. Round, 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 round. There we go. iPad lets me cheat. So, we have the orbit of the moon and the Earth. And let's just say, as the moon is rotating around this Earth, bring this just down to the center. There we go. As the moon is rotating around the Earth, it's following this path. So, assuming it's going clockwise, then we're saying at some point it is exactly over Texas, is exactly over Houston. So we call this time 0 seconds. Times 0 seconds. And then we say at 0 seconds it has a relative distance of 0 kilometers. What does this mean? It's saying the moon, the negative time passing is before reaching Houston. The positive is after passing Houston. So 1 second after we pass Houston, let's put that about there. 1 second after passing Houston, it tells me that we are 1 kilometer away. So the relative distance seems to be moving around this orbit. The moon, if the angle is perfectly aligned with Houston, once it passes, this distance is 1 kilometer away. And that makes much more sense. 1 kilometer away from its relative spot compared to Houston. And that says the negative distance is before reaching Houston. So before it orbited to Houston, we have negative 1 second. And it even tells me at negative 1 second, I am still 1 kilometer away, relatively from where Houston is. And then 2 seconds away, I am also 2 kilometers away. And then in the other direction, at negative 2 seconds before I got to Houston, I am also 2 kilometers away. So what is this telling me? My angles are off, but assuming that these are all equally spaced out. Not a great artist. 1 kilometer, 2 kilometer, negative 1 second, negative 2 seconds. So we're getting closer and closer. The moon's getting closer and closer to being over Houston. And then we're exactly over Houston at 0 kilometers. And then we pass Houston 1 second later. We are both 1 kilometer away from Houston 1 second after and before. That's profound, because this gives us an absolute value function, where it's both the same, 0, 1, 2, 3, 4, on one side as it is to the other. So, identify the parent function that best represents the data, write it in function notation, and graph it on the scatter plot. So, we have a parent function, and based on this table, 0, 0, 1, 1, 2, 2, 3, 4, negative 1, 1, negative 2, 2, this is the absolute value parent function. And I could tell if I plot those scattered points, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4. If I graphed a function through the scattered plot, that is most definitely the absolute value of x, the parent function, the most basic version of this function. Centered at 0, 0, the origin, its vertex. And then, so we got our function, we plot the scatter plot, identify key attributes including symmetry, intercepts, max, or min, and relate their meaning to the problem situation. So this spot right here, relating the meaning, is the most important thing to me, because I know you can tell me what the axis of symmetry is. I know you can tell me what the vertex is. I know you can tell me the intercepts and all that. This is a real-world instance, so I stole this from NASA. Imagine you're a mathematician, and you started working there, and there's some, I don't know, geologist or whatever NASA expertise engineer who sees this graph. And they're like, that graph means nothing to me. I haven't seen an absolute value function in a while. Why is it an absolute value function? Why is it centered at 0, 0? Why is it symmetrical? Like, you have to be able to relate all these things mathematically to a person that wants to know the real world meaning behind it. So to get full credit on my test, not only do you need to tell me the math, the mathematical answer. I also want you to tell me the real world. What does it mean in a real world context? Or at least in this problem. So, symmetry. Where is this thing symmetrical? It is symmetrical right at the y-axis. So, smack dab in the middle. It looks the same on either side of this y-axis. Same on this side as it does on this side. That is incredibly profound. Symmetry doesn't happen that often in nature, especially not perfect symmetry. So what does it mean for this side of the graph to look exactly like this side of the graph? Well, if I look at my picture, this is telling me 1 second after Houston, I am the same exact distance as I would be the same seconds before Houston. What could that mean? The only way that's possible is the speed I was going to get to Houston is the same speed as I was going after I get to Houston. Everything before I get to Houston is exactly the same. So the moon has a relative velocity of 1 kilometer a second. The symmetry, the mathematical symmetry at the y-axis, or the equation x equals 0, has so much importance to a NASA scientist in telling them, yes, turns out the moon really does have a constant speed. Because if this did not look like an absolute value function, that would tell me the moon speeds up and slows down. And maybe it does in the real world, but at least in this scenario, we need to tell the NASA scientists the moon goes the same speed all the time. And that is what we could see from the symmetry. It's the same on both before and after. So not only is the moon going at constant speed, you could keep going. The before, or the distance, oops, a little too big. The distance from the moon is exactly the same before and after Houston. And that's a very important fact. You should tell someone that that is what you're observing. And then we got intercepts. The only intercepts that I see on this graph, x and y, are when it hits the origin, 0, 0. So x equals 0, y equals 0. What does that mean mathematically? Well, it's the vertex, it's the lowest point, it's the middle of the graph. What does it mean in the real world context? Well, we look at our table. X is time in relation to Houston, y is the distance. So at 0 kilometers and 0 seconds, what's profound about this point, this intercept? That's the middle of the graph. That's where the moon is right over Houston. And you should tell someone that. If someone asks, well, what does the origin mean? What was important about those intercepts? Well, that's where the moon is over Houston. And we should know where that relative point is. And then max or min? This is a question as, is it a max or is it a min? And looking at this graph, it's totally a minimum at that origin. So we say, why is it important? Why should I tell someone it is important that 0, 0, the origin, that vertex is a minimum? It's not a maximum. What does that tell me? There is a shortest distance. There, you get further and further away from Houston. You can get further and further away, but there is a shortest distance. A shortest or closest distance to Houston. That's important to say, that there is a point somewhere in this orbit where the moon is directly over. We need to say there is a shortest relative distance. All right. That's how we do a very, very in-depth real-world explanation of the mathematical attributes of the absolute function that we're getting from both a table and a verbal description. Okay, next problem. Actually very similar to the moon problem. Absolute value lends itself really well when we talk about distance to a fixed point. So a car driving a constant rate of 60 miles per hour. So notice last time we said the symmetry was so important of the absolute value. The symmetry of the V is important because that tells me there's a constant speed before and after reaching a fixed point. And so much so, they even said constant rate of 60 miles per hour. This car is going the same speed all the time. Otherwise, this wouldn't work. The table represents the distance from a historical mile marker on the highway as a function of driving time. So, imagine we have the highway. We got some historical mile markers, so it's probably a sign. I don't know, maybe it's a rubber band ball, maybe it's a giant boot, maybe it's the Alamo. No, Alamo's not next to the highway. Something's next to the highway. Ghost house, haunted house, something like that. So we got our mile marker. We're driving. It looks like we have a driving time of 0 hours to 8 hours. So we have a start time. Let's say we start from here. Let's say at 0 hours, we go all the way to 8 hours. And we're driving. Vroom, 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 vroom. And my car starts at some distance away from the historical mile marker, gets closer and closer and closer and closer until we're right next to it. We pass it, and we get further and further and further and further away. So we can be the same distance away from the historical mile marker before and after reaching it. So what does that look like? At 0 hours, we are 240 miles away. So this is hours, and this is miles. So 0 hours, we're at 240. At 8 hours, we're also at 240. What happens at 1? So let's see if I could split this up. 4 is the middle, right? Right between 0 and 4, or 0 and 8. And then at 4, it even says the middle of our table. At 0, we go 60 in both directions, 120 in both directions, 180 in both directions. 0 is the middle. So at 0, we're at 4 hours driving time. So we are at 4 hours right next to the historical mile marker. We're right there. 0 distance. So, what are they asking us? We have a picture. We have an idea. This is an absolute value, absolutely. Which equation could be used to determine the driving times when the car is 150 miles? They just want the equation. Well, we need the equation for its distance. So, they gave us a vertex. That's the middle of the table. And what do I see happening? All you need to create the equation of an absolute value function is its vertex and its slope. So we have 0, 4. 4, 0. This is x, this is y. 4, 0. So we went 1, 2, 3, 4. 4 to the right. That's its vertex. What's its slope? Well, 1 unit away, so that's 4, that's 3, and then 5. At 3, we're at 60. And at 5, we're also at 60. So when I move 1 unit forward or 1 unit behind, I'm driving 60 miles per hour. That's our slope. So we have, how did I get to a vertex of 4? On the x-axis, I moved right 4. How do I show right 4? I subtract 4 on the inside. How do I show that slope of 60? I multiply 60 right in front. That's our a value, vertical stretch of factor 60. That's our slope. And this equation, it could equal y for any distance, but they want us to know, when is it 150 miles? Just set it equal to 150. When does it intersect 150 miles? And this would be the equation. And that's all they asked for, so this is technically our answer. But, quick run through of how to solve it, in case you need some prep for the test, because I know there are some questions where they do actually want you to solve this. Step 1, isolate. 150 divided by 60, the zeros are gone. 15 divided by 6 reduces to 5 halves. 15 divided by 3 is 5. 6 divided by 3 is 2. Yep. This is possible. Step 2, check if it's possible. Don't split it yet. Absolute value equals a positive number, 5 halves. A-okay. Now we split it. And we say x minus 4 equals 5 halves. This is how we get rid of absolute value bars, by splitting it. And x minus 4 equals negative 5 halves. Then we add 4 to both sides to get x by itself. And I'm going to do this math off to the side or on the calculator. I don't feel like thinking about fractions right now. Although fractions are let's see. 5 halves plus 4. 4 is 8 halves. So that is 5 halves plus 4 is the same as 5 halves plus 8 halves, because 8 divided by 2 is 4. So 8 plus 5 is 13 halves. So we got 13 halves. And then we have x equals negative 5 halves plus 4. So that's 4 minus 5 halves is the same thing as 8 halves minus 5 halves, which is 3 halves. So I'm not going to leave these in terms of improper fractions just because our x values are time. I bet I could describe these in terms of time. Well, 13 halves, that's the same thing as 1 half plus 12 halves, which is 12. Well, 12 divided by 2 is 6. So that's 6 plus 1 half, so 6.5. X equals 6.5. And then 3 halves, that's 2 over 2 plus 1 half. That's x equals 1.5. So these are hours. So when am I exactly 150 miles away? Well, 150 is between 120 and 180. So I'm between 1 and 2 and between 6 and 7. Looks like I'm exactly halfway between 6 and 7. I'm 6.5 and 1.5. So at 150 miles, that would be somewhere about there and here. At 150 miles, we would be into our trip 1.5 hours. And we would be into our trip 6.5 hours. That is when we're 150 miles away from the mile marker. There's 2 times where it happens, 1.5 hours and 6.5 hours. So these are both our answers. Okay? We are moving on to variation difference and percent error. Variation difference has another name that could be used sometimes in physics class called absolute error. I like using variation difference as its name just because I feel like it makes sense. The first thing I'm going to do is I'm going to fix this equation, this formula. You're going to have a formula on the test. It's not going to say actual. I chose actual because actual comes up a lot in these sentences. So determine the actual starting salary. It's actually very poor to use that word there, and it's my own fault because English is a Franken language, and actual means a bunch of things depending on the context. So don't use actual. I'm going to say what you're going to see on the test is measure. The measured value minus the average equals variation. Another word for variation might be the error, like how off were we? How off were we from where we should be? So variation or absolute error. So let's see a problem. Now, this problem does not need to be solved as an absolute value function. It's kind of overkill to put it as an absolute value function, but these situations are simple so that we can practice a complicated concept. There are times where absolute value used to solve problems like these, it's way easier to collect all our data into the absolute value rather than trying to do it in our heads. So, the average time for the athletes on the Central High School track team to run 200 meters is 27.6 seconds. So average time. What does that mean in reality? You took all the runners and they all averaged to 27.6. That's this average. And even more important than that, that's what the runners should be running. So if 1,000 people ran this track meet, or 10,000 people ran this track meet, I think I would assume that most of them would hit 27.6 seconds. That's what it means to be the average. This 200 meters should be completed, theoretically completed, in 27.6 seconds. That's our average. And then we have the error. Let's see. The slowest and the fastest recorded times variation from the average by 5.3 seconds. So what does that mean? The fastest runner and the slowest runner, they were off from the average. They weren't true and perfect to the average. They were off just a little. How much did they vary? 5.3 seconds. How much was the error from the average? 5.3 seconds. So what's measured? Measured is our unknown. Measured is the value of the slowest time and the value of the fastest time. We don't know what those are until we solve for it. and you could do that just by adding 5.3 seconds to that average or subtracting it to get plus or minus. What's the minimum? What's the max? So we say this unknown that we're going to define is the max, minimum and maximum time. It's the fastest and it's the slowest at the same time. How is it both? Because of the way absolute values work. I could write that unknown, the difference between the measured value and the average. Well, how far off are we? If 27.6 is the average, that's our midpoint. So you might see average set as midpoint sometimes. And the fastest runner is up here, and the slowest runner is over here. Well, what's the distance? What's the distance between the fastest value and the slowest value and the average? They're off by 5.3 seconds. So we could add 5.3 to get the slowest runner, or subtract 5.3 to get the fastest runner. Either way, this is an absolute value because you can capture this plus or minus as the absolute value of some difference. So how off are we? The one thing you'll notice, it does not matter if you write x minus 27.6 or 27.6 minus x. They are the exact same equation. That would be the same thing as me asking, is there a difference between the absolute value of 3 minus 4 and 4 minus 3? Well, no. 3 minus 4 is negative 1. Absolute value of negative 1 is 1. 4 minus 3 is 1. The absolute value is 1. The distance, the absolute value of a difference gives us the distance without regards to signs. So if you write this and all your answer choices look like this version, you know you're correct. You just have to flip-flop your numbers and they're still equivalent. The one thing that can't get flip-flopped is our variation. 5.3 seconds is the difference. So when we take the absolute value of this difference, we should be at 5.3 seconds. So if I solve it out, well, we can definitely equal a positive 5.3, split it up, and we see that this is x minus 27.6 equals 5.3, and it's the opposite. X minus 27.6 equals negative 5.3. Add 27.6 to both sides. And then we get, let's see, the slowest and fastest time. So fastest time, slowest time, the longest time that we should see at this track meet is 5.3 seconds plus 27.6. So slowest runner is going to have a time of 32.9 seconds. The fastest runner should be 27.6 minus 5.3, 22.3 seconds. That's the fastest race time. And the difference between these two values and the average is always 5.3. Okay, another way that this problem can be used, or absolute error or variation error, is in average salary, or really any average. Anything that has an average we could use this with, because we're talking about the midpoint. So we have a target value. To prepare for a job interview, Hinda researches the position's requirements and pay. Always find out how much you're going to get paid. She discovers that the average starting salary for the position is $38,500. So if you asked 10,000 people who have Hinda's job, or the job Hinda wants, if you ask them what their salary is, they should all have an averaged out to $38,500. So what does that mean? If you get this job, you should theoretically be paid this much. But we know that's not the case. Depending on how long you've been working or your job experience, they might pay you more, they might pay you less. Depends on a lot of factors. So her actual starting salary, what is she going to be paid in real life? The measured amount. If I looked at Hinda's paycheck, what does it actually say there? What is the measured amount? I'll say her true salary, her measured salary, her real world salary. We don't know what it is. She could be plus or minus, and it says could differ by as much as $2,450. So the difference between how much she could get paid minus the average, what everybody else should be getting paid, the difference between her and the target, her max and min, should be $2,450. How off are we by $2,450? Plus that or minus that? You definitely want the plus that, but it could be minus that. So if I wanted to solve for this for the min and the max, I would say, yes, this is possible. Split it. X minus 38,500 equals 2,450. And then we have x minus 38,500 equals the opposite, negative 2,450. And then we're just going to do some quick maths and add 38,500 to both sides. So because we're adding 38,500 to both sides, notice if I didn't have this written upside down, this is just 38,500 plus 2,450. And this one is 38,500 minus 2,450. That's where we get that number line idea of the average, the midpoint is 38,500, and over here is plus or minus the value of 2,450. So what do we get? What's the max she could get paid? The min she could get paid? 38,500 plus 2,450 is $4,950. That's the maximum she could get paid. What happens when I subtract 2,450? I should get, yep, that looks right, $36,050. So starting salary says 38,500, but she could get paid as low as this. But if they really like her, or she's have a lot of job experience, she could get paid as much as this. Just depends. But that is within this acceptable error amount of upper, give or take, $2,450. Next, we're moving on to percent error. So this says many times experiments and data collection results are judged by comparing actual values to values by determining the experiment or data collection using percent error. It's a fancy way of saying, let's say you found a weight set, like 45-pound weight set. The thing should weigh 45 pounds. And in actuality, it weighs 45.5 pounds, so it's off by 0.5. Then how much off were you? How much off is 0.5 from the actual 45 pounds? So that's where percent error comes in. How much off were you? So 0.5 divided by 45 would give me approximately 0.01 repeating. So I would say that, move that over to 1, 2, that's about 1% off. About 1% off. So your error, your error is 1%. So what am I going to do? I like to say percent error is human error. That's a very helpful way of remembering which parts go where. In theory, something should actually equal something. And we know that's not true. So in the real world, in math, you could say that this board is 12 inches long exactly. It should be. Theoretically, it is that length. But in reality, the observed value, if you observed the length of that board, or if you measured it, or if you did an experiment and then you measured it, this is called the experimental value, the measured value, the observed value. If you actually did the measuring and pulled out a ruler, checked, it might be, instead of exactly 12 inches long, it's 12.2 inches long. So how off were you? And then you find the difference between what it should be and what it is measured in real life. Take the absolute value of that difference and that number out of the theoretical value, the actual value. How off were you? By what ratio? By what percentage? And this 100, I'll explain why it's there in just a bit. But it has to do with the percent symbol. So first, we formulate an absolute value equation to represent the percent error for the data collection activity performed by the student groups in Mrs. Paxton's geometry class. So what are these kids doing? We need to make an absolute value equation based on what they're doing. We're going to use this formula. Groups of students in Mrs. Paxton's geometry class collected data on the diameter and the circumference of various circles and use the data to estimate the value of pi. Estimate the value of pi. They are measuring, they are observing and experimenting. What is their value of pi? Students then determine their percent error using pi equals 3.14 as the actual value. So this is the theoretical. Theoretically, pi should always be 3.14 something something something. These kids are measuring circumference and diameter and calculating pi themselves. So what are they doing? Circumference is 2 pi r, but 2 times radius is diameter, so circumference is pi diameter. Well, the kids are picking up a Pringles can or a water bottle or any kind of circle, and they're measuring the circumference and the diameter of that circle. And then they're solving for pi. So they divided both sides by d, diameter, and they see that pi equals circumference divided by diameter. So if your circumference is off, like let's say the kid takes a ruler and tries to bend it around the Pringles can. The ruler doesn't bend perfectly, so the circumference is way off. But they're like, circumference is about 2 inches. And then they say the diameter is about 1 inch. And then they tell me that pi equals 2. They are crazy off. Pi should equal 3.14. And we're going to say, how much are they off if they say pi is 2, but the actual is 3.14. That's where percent error comes in. How much are these kids off if they do some real world measurements? So we formulate our absolute value. Percent error equals the theoretical value of pi. So off to the side here, you could write actual minus observed, that difference between those two in the absolute value bars, or you could flip the order. And there is no noticeable difference. Because if you take the difference of two things and flip-flop them, one of them is going to be positive, one's going to be minus, depending on which is bigger. But if you take the absolute value of both of these things, they're exactly the same. So I'm going to write, instead of actual minus observed, I'm going to say the kid's experiment. We don't know. Our unknown is, what are the kids' measurements? What are the kids getting for pi? We don't know. So I'm going to say x minus. I'm going to put the observed, the experimental value first. Why? Because I don't feel like dividing by a negative x at any point. So x minus the actual, the theoretical value of pi, the problem tells us to use 3.14. So take the difference between those two things, and that value, the error out of the actual value of pi, should give us the relative error. How do we get the percent error? We multiply by 100. So what is this 100 doing? We're going to see right here. What observed or experimental values of pi would yield a 10% error? We don't have to write the percent symbol because there is 100 here. That's the only reason multiplying by 100 is there. So I'm just going to replace PE, percent error, with 10. 10 equals the absolute value of x minus 3.14, all out of 3.14, times 100. So why is this 100 here? If I divided and isolated, got rid of the 100 right now, then 10 out of 100 is 10%. That's 0.1. 10 is not 10%. Old school 8th grade math, 7th grade math, elementary math, to say 10% is really 0.1. So why is the 100 there? So that I can just write 10. I don't know why they added it in there, but it is there. So we have isolate. What values of pi would give us a 10% error? Let's see, what would the kids get? What are the kids going to measure? Get rid of the 3.14 and the 100. I'm going to do it all in one fell swoop. Dividing by 3.14, the opposite is multiplying. Multiplying by 100, the opposite's dividing. That is the reciprocal of those two things. And then we have 3.14 out of 100 times 10. So that's gone, that's gone, that's gone, that's gone. And we are left with the absolute value of x minus 3.14 equals, let's see, 10 divided by 100, so the zero's gone. I'm left with 1 times 3.14, so that's just 3.14. 3.14 divided by 10, move the decimal place over 1 time. So that's 0.314. Or you could have just used your calculator. This is possible. 0.314 is a positive number. Split it, we get 0.314 equals the original And we have negative 0.314 equals x minus 3.14. Add 3.14 to both sides. And we see that the kids, to get 10% error, I'll just write it like this, x equals. What values of pi could our students get so that they are exactly 10% error off? Well, 0.314 plus 3.14 is 3.454. That's way bigger than pi, but it's pretty close. 10% off. That's not too bad. And then 3.14 minus 0.314 is going to give us 2.826, which, although that doesn't look like pi, it's got a 2.8, it's just as close to pi as this value is. They are both equally close. 10% off close to pi, 3.14. So what are the kids getting to get 10% error? They're saying that's pi, and they're saying that's pi. Those are the two ways to get 10% error away from pi. Now, Mrs. Paxton told the class that they must have a percent error of no more than 25% to receive a passing grade on the activity. For what interval or intervals of values will the students receive a passing grade? Well, that means the kids have to be within 25% error to get a passing grade. So if they are way off, they won't pass. But if they're just within 25% error, they're going to pass. So what does that look like? This phrase, no more than 25%, all we do is we take the same equation, x minus 3.14 over 3.14 times 100, just because you could just erase the 100 right now and then write it as a percentage. So I'm just going to multiply by 100, show you how it works, is less than or equal to 25. So that's how we stay no more than 25% error. Because we can be 25% and you'll pass. You're right on the edge of it, but you'll pass. But we should be below or equal to 25%. So why do I have the 100 here? If I divide by the 100 right now, I could just say we are less than or equal to 0.25, 25%. Then multiply both sides by 3.14, and we get the absolute value of x minus 3.14 is less than or equal to 0.25 times 3.14 is 0.785. 0.785. All right, we're going to take that value, and we are going to see, is it possible? And yes, of course it is. Why is it possible? Because we have an absolute value is less than or equal to a positive number. And there are positive numbers that are less than or equal to this positive number. Totally. So we say, split it. X minus 3.14 is less than or equal to 0.785. This is the original. And then we say x minus 3.14 is greater than or equal to negative 0.785. So we have to remember, when we're doing inequalities for absolute value, when you introduce the negative, the inequality switches directions. Then we solve. And notice now all I have to do is add 3.14. This is because of my choice of flip-flopping around the formula and having the observed minus the average, or observed minus the theoretical. And what do we get? That's gone, that's gone. X is less than or equal to something. X is greater than or equal to something. And we get 3.14 plus 0.785 is 3.925. That's a value of pi. And then 3.14 minus 0.785 is 2.355. And if I look, we're at 25% error. 3.925 is way worse error than 3.454, and 2.355 is way worse error than 2.826. Way too small compared to pi. But the kids are going to pass because these are within 25% error. And this is going to be an and statement. And if you can't tell, just draw a number line. Where are my values of pi? greater than or equal to 2.355. So greater than or equal to, closed circle to the right. And then we have less than or equal to 3.925. That's closed circle. Sorry, closed circle for both. And they meet in the middle. This is an AND statement between these two values. So pi could be as big as 3.925 and as small as 2.355, and you will pass. Any value between those two values, and you will pass. The final statement, what happens when the students get 3.14 as their value of pi? What if they experiment, they measure, they observe, and they see that 3.14 is their exact value of pi that they're getting? Well, what happens? What's the percent error if they get it perfect, dead on the money? Well, there is no percent error, because 3.14 minus 3.14 is 0. Absolute value of 0 is 0. 0 divided by anything or multiplied by anything is just 0. If you hit it right on the money, we hit our target, the average, the theoretical, then 0% error. And that's it for the notes. Good luck on the test.